Okay, I'm trying a new technique with my iPad and making a explain everything video. So we want to compute the minimum velocity just to make the curve. And I've drawn the picture here already. And for the case of just making the curve, there are three forces when friction is present. There's the normal force, we'll label that as N. There's the weight, which is mg. And then there's the force of friction. Now the force of friction is acting up the incline. It's keeping you from sliding down into the ditch on the right. So if you went too slow, there wouldn't be enough friction and you'd slip into the ditch. The frictional force, I should say, wouldn't be enough. You wouldn't have enough friction. Okay, so we'll start by doing what we do all the time. And we're going to draw a free body diagram over here on the right. So we have our object, which is the car. And let's go back to red. And there's a normal force. And I'm drawing it by hand. You can see the normal force. There's a frictional force, like so, force of friction. And then, of course, there's mg, the weight. And I'm going to superimpose a coordinate system. And again, because it's circular motion, the inward direction towards the center of the circular motion is important. So I'm going to draw my coordinate system like so. And I'm going to define inward and plus y. And I can notice that the theta here, and there's a theta here. So that's my free body diagram. So like in these kinds of problems we've done before, we're going to consider the inward direction as well as the vertical direction or y direction. So let's look at y first. We'll write it over here, y direction. And we can say that MAY is 0, and that's going to be equal to n cos theta, which is this component. We'll do it in a different color here, right here, like that. And then there's a component of friction, which is like that's upward. Let's go back to black. So it's plus the force of friction times the sine of theta minus mg. And it's net force 0 in the y direction because the car doesn't slide vertically up or down. It doesn't slide up and down at all on the incline. So we can remember that the normal force plays a role in the frictional force, and we can now solve for the normal force. So the normal force is equal to, we'll do a little algebra, mg over cos theta plus mu sine theta. So there's some algebra here. I moved this, let's go to a different color, move this over. And then I divided by, factored out the n, and then divided to get this expression for the normal force. Okay, let's see if I can go to the next page. Well, that worked okay. Let's try it. Okay, so now we need to do, we'll go back here, right? We're going to do the inward force. Okay, so the inward force is mv squared over r. We know the radius of curvature of the curve. And we know that for circular motion, the net inward acceleration is v squared over r. Well, if we go back here and we look, we can see that there are two components, right? There's a component here, and there's a component here. Notice that the normal force component is inward and the frictional force is outward. Okay, so we can write, go back to black, that it's n sine theta minus the force of friction cos theta. And so let's just slide over here. You can see it's the normal force is the sine, it's opposite the angle, and the frictional force is cosine, it's adjacent, which is what we have. So we have mv squared over r is n sine theta minus mu and cos theta. And we could substitute in n. Remember that we wrote n is mg over cos theta plus mu sine theta, right? That was our expression right there, mg cos theta plus mu sine theta. So we're going to just substitute that in, and we can write that mv squared over r is mg times sine theta minus mu cos theta over cos theta plus mu sine theta. Okay, and the m's drop out, and we get that the v squared, this is the minimum velocity, is rg sine theta minus mu cos theta over cos theta plus mu sine theta. So notice that the numerator here is actually smaller than than before. It was just sine theta before, and as mu gets bigger, the numerator gets smaller because of the minus sign. The denominator gets bigger. So as the frictional force gets bigger, the minimum velocity gets smaller. Notice that when mu equals 0, if there's no friction, we could write over here mu equals 0, we would get v squared equals rg sine theta over cos theta, which is rg tangent theta. That's exactly the no friction case we got before. Okay, so our expression for the minimum velocity depends on the friction, and it depends on it the way we expect. Let's try playing this back.